Our next speaker is Dr. Faisal Abbas. Faisal is a research associate in CMAC, and he's working on the Made Smarter digital medicines manufacturing project. And he's going to tell us about tablet manufacturing DataFactory for high-throughput experimentation. Yes.
Thank you very much. All right. Hi, everyone. So my name is Fess Daniel Markle as our platform lead. So I would like to start off by explaining the typical challenge that we see in the process of medicine development. So as we come across a new API, in order to produce a stable tablet, we need to think about the choice of different excipients and their concentrations. So one of the main challenges that we have highlighted is that the experimental load in this case increases as we come across different, like multiple choice of excipients, and where we have to maximize the drug loadings and optimize the process settings. So in this case, what we are proposing is a model-driven approach where the models can inform that the system what experiment or what parameters we need to use to run that specific experiment. That's something we are hoping can lead us to reduce the time and the cost associated with it. But obviously this concept cannot be achieved without having a digital transformation. And this is why we have established a fully automated system that can produce a tablet starting from the raw material side to taking any kind of NIR scan or measuring the weight, and then moving on to the compaction that we use to produce a tablet using direct compression technique, moving on to the post-compaction, which is mainly about the tablet testing and capable of testing the tablet weight, dimensions, and the braking force, and then moving on to some advanced level testing, which is about the sisal drop in this case. So as soon as we collect all the data from this stage, we move on to this data collection that is actually driving this experimental agent. So now, the way we have designed our experimental agent that's running all the experiment autonomously can be used in two different modes. One is in which a user can define all the list of experiments and hit the start button, and literally the whole system can go through all the experiments, all the parameters one by one, and gives you all the data like as a result of that experiment in a Microsoft SQL database or in an Excel sheet. Or you can use this system in a self-driving mode in which the model, you just have to define the target, and the system will iterate itself to reach that specific target. So the system at the moment that we have developed is capable of handling any kind of inappropriate dose, and also the system can repeat any of the experiment in case the data is not complete. So the main target is on collecting a high quality data out of this. And eventually the goal is obviously to reduce the lead time and the waste, and by increasing the productivity in this case. So making the whole system fully automated is not the only target in this case, but in fact we are aiming to help other researchers as well in this case. For example, one of the main workflow, as I have already explained, is the tableting and the testing, where we produce a tablet, we test it, and that's it. But what if someone does not want to test the tablet at the same time? So the second workflow is about tableting and then the storage. And then obviously we have like number of different possibilities in different workflows. One of the successful workflow that we have implemented, and that is there working in a fully automated mode, helping one of the PhD, is NIR spectroscopy, where the PhD researcher is using a robotic arm to acquire the dose from the dosing unit, run the NIR spectroscopy on it, and release that sample in a vial for any future testing on it using HPLC. So that's how we are transporting the powder using this custom-built transportation unit that's comprised of this tube that carries all the powder and driven by a linear gate. And one of the key elements about this transportation unit is that if you have a look on the bottom side of this transportation unit, then there is a 10 millimeter wide sapphire window that literally allows us to scan through the sample using micro NIR, as I explained in the previous slide. So all the instruments that we have used, they are fully integrated with the supervisory control unit, which means we can read and write the data in the real time. So this is a very short video. Obviously, does not show the whole process, but a glimpse of the whole process in which the robotic arm moves from platform to platform to capture the high quality data. Feel free to join me for a live demonstration around 11 o'clock. So we have tested this system over the range of different formulations comprised of paracetamol as an API and choice of different excipients like lactose, mannitol, DCPA, and MCC in different concentrations. So the first thing we tried to analyze was the NIR spectrum. So obviously the raw spectrum doesn't make any sense. So we have to do some kind of pre-processing on it. In this case, we have applied the first derivative, sophistically first derivative on it to remove any kind of unnecessary offset, and then we apply the PCA to see if we can find out any kind of segregation between different compositions. The next thing we have assessed is the powder dosing, because this was one of the main concern in this case, that what is how effectively we can transport the powder from one station to the another. So in this case, as you can see, we have tried that over the range of different formulations, and the powder loss stays within 20 milligram in this case. Again, we have done the same assessment, but with the different dose weights to see if the higher dose weights can impact the powder loss, but it turned out to be quite consistent. The next case is running the system in an automated DOE mode, where again a user can define list of experiments based in PharmaMV. So the system is also integrated with the PharmaMV software, where we have developed that dashboard, which the user can use to interact with the system to define all the experiments. So in this case, we have ran this system in two different test cases. The test case one is in which we are interested to run the experiments over the range of different pressure points and different dwell time. And the test case 2 is in which we want to use different dose weights over the range of different pressure points. So here are some of the results. That shows the tablet compactability, compressibility, and the tabletability profile, showing the relationship between the tensile strength, porosity, and the different pressure points. And the results are quite obvious. Obviously, as we increase the pressure, the porosity decreases and the tensile strength increases. Same goes for, here are some of the results with the test case 2, in which we try to implement run some experiments with the different dose weights. So one thing we can obviously see out of this whole automated DOE is that this automated tableting and the testing took almost 3.5 hours to cover 6 different pressure points and 3 different dwell time, compared to the manual testing that takes almost a day to cover the similar points. So this is almost a 50% reduction in the time. The last bit about the self-driven experimentation, obviously we use the same automated system, but on the top of that we have integrated a Bayesian optimizer. So in this case, the objective is to achieve a specific value of porosity in the tablet. And the parameters we want to optimize are the pre-compression, main compression, pressure, and the dwell time. So obviously the system will iterate itself through like different experiments to achieve that specific porosity. We have tried that concept on the range of different target porosities, 10%, 15%, and 20%. So on all the graphs you see on the top side of this this slide shows we are reaching to that specific target. For example, in this case it was 10% within like 12 iterations, which are not going to take longer than 10 minutes. Same goes for 15 and 20%. All the graphs at the bottom hand side shows how the system actually moves within a search space of different process parameters that we want to optimize. So the system starts from this point, iterate through different points, and finally we find the target somewhere over here. And same goes for the other target points. Last bit is about the automated sisal drop testing. But obviously, first thing we have to think about is how we can separate the damaged and the undamaged tablet, because the main source that takes that spit that tablet out of the system is the automated hardness tester, but that produces the damaged and the undamaged tablet at the same time. So we need a custom built tablet separator. So in this case, this tablet separator will use that motor-driven mechanism to align this tablet precisely within this narrow pathway from where this second robotic arm can pick this tablet up, to place it further on for further testing. And all the damaged tablets can be collected on the other hand side of the tablet separator. And then as soon as we receive the tablet over here, we move it over to this platform where we discharge that liquid using this automated syringe. Once we are done with that testing, obviously, again, we use this robotic arm to move that tablet into a waste bin. So that's, again, a very short video, shows how the tablet arrives in that small tablet separator and how the robotic arm picks it up to move it on this automated Cecil drop platform. And obviously, based on predefined value for the duration of the video that we want to record for the assessment of investigation of swelling kinetics. Initially, we dispense that liquid on the tablet, and then in this case, the video length was defined around 120 seconds, and you can see that how the tablet is swelling upon coming in contact with that liquid. Happy to take any questions, and like I said, the live demonstration will be on from 11 till I think around till 12. Yeah, and the poster number is 25. Thank you.
Okay, thank you, Faisal. That was really interesting. Does anyone have any questions? Can I ask one about the near infrared? So you're using near infrared to monitor the blend. Are you using the near infrared to monitor the blending in real time?
Yes.
Okay.
Yeah. So there are two. There could be like multiple purpose to use that NIR spectroscopy. One of the main reason was to use it to identify any kind of blend homogeneity.
Yep.
If there is any like non-uniformity in the blend that could be identified, so that instead of using that same powder for producing a tablet, we can recycle that powder,
okay,
blend it again, because in the future the plan is to like have a automated blender as well in the place, so that the decision could be taken in real time and we can release that powder back in the blender, blend it again, and then keep doing that until we are satisfied with the blend homogeneity.
Okay,
yeah,
that's nice. Yeah, thank you. Kevin, thank you.
Hi there. Nice presentation. In one of the graphs you showed related to dosing weight versus what the actual dosing thing delivered, it seemed like there was a systematic underdose or overdose. It was hard for me to tell from the graph. I think it was underdosed, but
probably in this case.
It was back a bit. There was like a almost like a Pareto plot of the.
Or you might be speaking
there,
about
right there. Whoop.
This one?
Yep, exactly.
This one, right?
Yeah, so is that like hard to correct for? Is there something that's like, preventing you from getting those points on the line?
Okay, so basically this is somewhere we want to investigate the source of errors in the system. So as you can see, so mainly because the graph is between the powder that we obtain from the dosing unit and the final weight of the tablet. So in this case, we are currently seeing some fluctuations in terms of dosing the powder. That's based on the properties of different materials. Could be because of the different physical properties of the material. So yes, we do see some fluctuations, especially with blend number 6. I think that's comprised of probably DCP and MCC. But we are aiming to obviously make some improvements in the current system. Like I said, in the future, the whole dosing system is going to be replaced with a new system where we will be having 5 different hoppers where we can prepare that blend from scratch. Because at the moment we are assuming that the blend that we are using is prepared by a researcher manually. So we use that blend to produce all the tablets. But this is definitely going to be replaced, yeah, the new system.
Hi, really enjoyed the talk. I was interested in your free Bayesian optimization graphs. It looked like the algorithm was very exploitative and hadn't explored the space very much. Are you confident that it's found the true optimum in those systems?
Yeah, that's a very valid point. But obviously, as soon as we achieve that, we haven't thought about it yet. But because mainly the target was on like achieving that specific objective function. But one of the another suggestion that I've got from one of the colleagues during the event is that obviously we are producing only one tablet and we are not that confident for that specific solution. So another thing we can do is, like in the future, is as soon as we achieve that target, we can probably maybe produce more tablets to build up more confidence to make sure that that point, the solution that we have received from the optimizer is actually the optimum point and causes like maybe less fluctuation. Yeah. So there is something that we may need to like think about here.
Great, thanks.
There is one.
So,
That side.
all right, okay. So mine's a follow-on one actually to the previous one. So it's just a question. It's more my ignorance of optimizers. If you start in different places, I was just wondering if that then, as a way of saying, well, have I explored the space? If you start somewhere different on your plot, does it end up in the same place, or does it end up somewhere different?
All right. So your question is, I think, mainly related to the starting point, right?
Yeah, it was. Because you started sort of top left. If I start top right or far back, it's just a question of ignorance about how Bayesian optimization probably works, I think.
So basically, in this case, the starting point is very crucial because we are not like picking up that starting point on random basis. So that suggestion basically comes from the Bayesian optimizer, which is obviously built on the history of data. So the first suggestion comes from that side. We run the experiment, and that's where the system actually run the further experiments from that point onwards. But eventually I'm not too sure if we force that starting point a little bit different from the one which is suggested by the Bayesian optimizer. What's going to happen? I'm not too sure, but yeah, ideally it should reach to that same point, I'm assuming. Yeah.
So I'm going to bring this back to the near.
Blend or the calibrations?
Well, your calibration is, I assume you test it on a blend and it works, but if you make any changes to the blend, do you need to do anything with the calibration?
Okay, that's a very valid point. So again, we have another PhD, Alex, who's working on this stuff. So again, he's working on some kind of models in which he takes all scans on the raw materials. Again, preparing a model that can perhaps predict the spectrum for the potential blend. So, for example, if each of the blend was comprised of paracetamol, DCP, lactose, so what he's actually trying to do is calibrating his models based on the individual scans taken from lactose, DCPA, mannitol, and based on that, he's trying to predict that. And I think if you visit him on his poster, he might have presented some of his results on the poster that this predictive technique was quite accurate, like above 98% or something like that. So yeah, I'm not too sure if that has answered your question related to calibration. One more thing I want to highlight is that obviously that the NIR scan may be impacted by the dark and the reference scans. So because previously what we used to do is take the reference and the dark scan only once and keep running the experiments all the time, but that actually changes over the time. So with the help of robotics, obviously that's not too much of work for us. So we have permanently attached that 99% reflectance disk on the robot. So it's like before producing every tablet, before scanning any sample, we do that reference and the dark scan to make sure it is like consistent over the range of different experiments.
Okay, I think so.